So, all right, let's start. So hi everyone, my name is Shaifi. I'm gonna quickly run on a really basic 32-bit Windows stack buffer overflow, also known as stack smashing. What the purpose of this session is to understand the vulnerable codes, especially in C, where actually some of the C function doesn't have bound checking. It means if you write something, if you do some inputs, let's say it's supposed to take 30 characters. Instead of that, if you write more, it will not check it, and it will intake the whole 60 characters. So this is just myself. I'm doing cybersecurity masters from Latrobe. This is my LinkedIn profile. This is my Twitter and Hack the Box. Feel free to connect with me. So over here, I already have a binary called chat server. And we're going to exploit this binary. So what we can do, so from your Kali machine, if you, let's say you're targeting a machine and you'll come across some sort of binary, you feel like this could be a buffer overflow exploitation can be done. So you can transfer that file via probably web server or SMB server, how you want to transfer it. And then you can analyze. So there's a different ways you can analyze. You can launch Ghidra if you want to do it. This is a little bit advanced. I'm not gonna go there. So what we're gonna do, we're gonna do strings, and we're gonna. So if we do strings in the chat server, that's gonna show me the functions within this binary. And from here we can actually find out, let's say, what we need to find out is what is the port it's actually listening. So I'm using a binary from brainstorm room in Hack the Box, and see you can see it's going to listen on 9999. Okay, so now what are we going to do? We're going to transfer this file to our Windows machine, and then trying to develop the exploit and locally from my Windows VM. So if we go, I already transferred that. Hang on a sec. I already transferred that in my, if I put it in here, chat server. So this is the binary. Always remember, like if you're targeting a machine when you see exe file and you feel like this could be a buffer overflow. If there is a similar thing, like here I can see like essfunc.dll. So always try to copy all the files relevant to the binary. Sometimes DLLs are mandatory to run, sometimes it doesn't. So like I have came across some, like it's just standalone binary which runs a server, but this one requires a DLL to run. So without this DLL, it's not going to run properly. So what we need to do is we need to launch this as administrator. So whenever you transfer in your Windows, you need to launch the server as administrator. And one more thing, when you're developing exploit locally, always like disable your defender and antiviruses, because otherwise your defender will flag these vulnerable binaries and you can't develop exploit. I can see some chats. Hang on a sec.
Yeah, it's actually nothing. You please continue, Shaifi.
Okay, because hang on, let me get the windows up so that I can actually answer if actually if anyone has any questions, can you just turn on their mic and ask the question? Probably that'll be easier for me, if it's all right. Okay, so let's continue from here. So where was I? Yep. So disable your defender, antivirus, and then transfer the files. I think you can use web servers, you can use SMB servers. If you want on, I can show you quickly actually before I even go there. So if I do this, so I'm actually trying to run in-packet SMB server, where you have to mention a share. So I have named that as red. So, and if I go here, sudo if config. So this is my IP address. CMD CD stop. So I can actually copy like that. 192.168.108.128. Then I have to name the share, and then you just need to whatever you wanna copy. So it was chat server.exe. So you will see this chat server has been copied. So via my SMB server. So you can transfer it like this if you want, or you can launch a web server in your Kali and transfer it. Okay, before so I don't need that. So let's run it as administrator. So always remember to run it as administrator, because otherwise I'm using a debugger called Immunity Debugger. So you have to run both these programs as an administrator. So let's run this one. So this is so this is Immunity Debugger, and what we need to do is we need to attach the server to this one so that we can debug. Attach chat server, attach. So now the server is running from here, and look at on the right bottom corner, it says it's paused. If I'm going too fast, please let me know, so that if you guys have any questions so far, just ask me. I think, because otherwise I would not know actually you guys are understanding or not.
And Shaifi, I got a question to the participants. Is the screen visible for you guys? Like,
sorry.
I'm like, is it visible, the screen? It's okay for me because I'm using the laptop.
Yep. No. Oh yeah.
Yes, I can see it.
You can see the windows, right? Because this is crucial.
Yeah.
Yeah.
Okay, cool.
Okay. So basically these are the registers. Okay, and these are the functions here on the left side. So later on, when we're gonna actually poke into the server, when we're gonna send more characters, it will see a change around these registers, and then from here we need to actually, or we'll develop our exploit through this platform, let's say. So we can see it's paused. Now what we need to do is we need to actually make it running so that we can actually interact with the Immunity Debugger. So let's play this button. So see, it's running now. And now let's go back to the Kali machine. So what we can do is actually, because the server is running, we can always use Netcat to actually connect with this one. 192.168. I think that 29 was my IP address. Let me quickly check that. Oh, not that. Sorry, pardon me. CMD. 129 is my IP. And remember, we found out the server actually uses quad 9 as a port. So if we connect with that, so see, we can now interact with the server from our Kali machine, which is running on the Windows. So from here, if we're encountering something, you can test it manually. And there's another couple of other ways we can do, that's called fuzzing. That's actually depends on how critical binary you are actually encountering. So if it's too many functions and the server or the binary is asking you too many inputs, then we have to develop another Python code to actually fuzz. I'm not gonna go in there. That's gonna be that's pretty advanced level. What is it asking? It's asking for a username. Let's give it a admin, and then it's asking for a message. If I just write some, okay, it's still asking for a message. That means it's working properly. So if we go back to our immunity, see, nothing's unordinary actually happened here, right? Now we need to try to find out where it is actually vulnerable, either in username section or in message section. So let's target the message bit. I'm going to generate actually 5,000. I'm going to generate. Look, I have done this binary before. So normally you can target a section and start putting inputs in a way. Let's say 500 characters, 1,000 characters, 1,500 characters, and then you have to test it over and over and over, and then trying to find out. I'm going to try put 500, actually 5,000, if I'm not wrong. Hang on a sec. Like so. Copy that. If we put that, so see what happened was, before, when we put normal message in there, it exited normally and it ran again, right? But when you put way too much characters in the message section, it got hung. So if we go back to our Windows and have a look at, see, the immunity debugger has changed. So if you see the registers here, EAX, ECX, EDX, EBX. So ESP is one of the important registers. I don't want to go really deep into that, but let's say this is a stack pointer, ES. So this points to your stack space in your memory. And then see, EIP is the main thing we want to control. So because from EIP, we can use this address and we can jump to a next function. So I'll explain it later on. But now we can see the whole stack's been written with lots of A's, right? That means we have a vulnerability in the message section of this binary. So from here, what we can do is actually we can start developing a Python script to actually identify which part it's actually vulnerable, how much actually it's taking to override this EIP section. Can you guys see it? Sorry, can you guys see the EIP here?
Yep.
Yeah. So we're trying to actually find this EIP address, and we'll build the exploit from there. So we have to now close everything again and run everything again as administrator. So when you develop an exploit for buffer overflow, you have to do every step from the beginning. Like you have to start the binary, you have to start the immunity debugger, you have to attach it every time, because when you hit the stack and it's actually errors out and gets hung. So all right, let's run it again. So now what we can do, there's two ways. Now we need to actually find the address of the EIP. So there's two ways we can do. One is manually, like let's say we can put half, like 25,100 A's and 25,100 B's, and trying to find out which part it's actually overriding EIP, either it's A or B, or if we and then divide that again and then divide it again. You know what I mean? You guys understand? Like, so if I instead of, let's say, instead of printing 5,000 A and
just a quick question, Shaif.
Yep.
So are we doing this so that we can then, because if it's all A's, we're not going to know where to target, but by using A's and B's, we can then differentiate the spot where we need to focus on?
Yes, the main focus for us is to actually trying to find actual memory address of the EIP.
Yep.
So
Gotcha.
when we input our characters, like extensive amount of characters, which actually overwrites EIP and then goes to ESP, right?
Mm-hmm.
Previously we saw. So we need to find out till how many characters we can actually touch the EIP.
Okay.
So what we're gonna do is then we're gonna put that exact amount of characters so that we can touch EIP, and then we have to find another function. I'll show it later on, and then we'll put that memory address in the EIP, and that EIP will link back to our shellcode. Does it make sense?
Yeah, so we're trying to land exactly on the EIP.
Yes.
Okay,
yes.
cool.
We're trying to land on EIP, and then we'll use that landing space, and then we'll I'll explain it. I'll
cool. Awesome.
Let's run it. Hang on a sec. So what I was trying to say is, if we do this way, let's say I'm literally dividing 5,000 to. So if we make it like this, we can always send this. We can always send this. Well, why I'm discussing about this is because sometimes when you encounter a machine, you might not have a proper environment to do MSF or some other tools, might not, and then you may have to develop these exploit within your target machine. So these skills then come to handy, because I encountered a machine where the machine itself was running GDB, and I had to develop the exploit within that machine. So I had a really limited amount of resources which I can actually use. So if we do this way, and then we just need to divide like over and over, it will take 7 cycles, I think, to find out the actual spot. Any question on that part? Probably not. Okay. Let's clear it. Oh, can write. Oh. All right. I have already created exploit script to save some time. So I'll explain this. So this is Python script. Through this Python script, we're gonna actually send what we did before with netcat. So now we're sending 5,000. Let's because the username doesn't really matter, so I wrote whatever. Now we're sending this script. Actually, let's start from the beginning. Actually, so this why I have an argument with the script, so that let's say I'm developing here in my Windows. Later on, I might have to target that other machine, so that I don't have to hard code that host name in. I just change the IP address while I'm actually giving the running the script actually. Anyways, so I'm sending a message block of 5,000 A's. So, and this, if you guys don't know, this socket module actually establish a connection. It's TCP connection to one IP to another IP, and then we're connecting with our host, which while our like giving it an argument, and the connection will be in 9999 port. Then we're receiving. So this part is a little bit important. Why? Because let's go over here. If I run netcat again, see, once I run this command, it replies me back with this, right? So that means I'm receiving something. So while I'm establishing a connection here, then I'm receiving. It's a little bit important because it depends on the binaries. Sometimes you need to identify how many times you want to receive, and sometimes it doesn't really work. So if you don't receive here, you won't be able to run this whole script smoothly. Am I clear? Any questions? Okay. So from here, so we're targeting this port. And then we're gonna send our username, which is here, and then we're gonna send our message. So what we're gonna do, we're gonna actually let's run it actually. Oh, sorry. So we need to do Python exploit 192.168. If I'm not wrong. So see, it's sending buffer, and if we go there, it's the same thing we did with netcat. Exactly same thing happened. Now we need to actually find out the EIP. Let's find it out. So before that, let's start the chat server again. Run as administrator. Run as administrator. Chat server. Running. Okay. So now what we can do, we can generate, we can use MSF pattern create. That's a Metasploit module, and see, and for a character length, we have given 5,000. So if we do that, it's going to generate special characters. See, it has generated some special characters which we can send instead of our 5,000A. So if we do vi exploit.py, so here we can literally put it this way, like that. Okay. Right. So if we run it again, see now instead of lots of A's, it's been written our created pattern, right? See the ESP bit. So now what we need to do is we need to write down this address, and then we need to find out which of the pattern actually overwritten this memory address of 31704330. So 31704330. Okay, so let's start it again. sorry, attach, etc. attach, and it's running. So let's go back to our Kali, and now we can say there's another Metasploit module to find it out, which is MSF, sorry, MSF thing, pattern offset, yeah, turn offset. So we can, our length was 5,000 and our address is 3170430. So see, now it has given our exact match. Offset is 2012. So it's actually telling us that that EIP address is actually located after 2012 characters. So now we can justify and we can actually identify whether this is right or wrong. So yes, it's running. So now we have to make a change in our Python script again. Actually, clear this one. Yep. So if I do vi exploit.py, now I need to, so what was it? Equals to, now we found out that our EIP is actually located after 2012 bytes, right? So what we're gonna do is we're gonna send 2012 A's, and then we'll see whether we have we can actually touch the EIP or not. So and we're sending everything as a byte. That's why we'll do here B. Let's say B, and then we're doing 2000 A's, if I'm not wrong. Yep. 2012. So now we need to actually see whether we can actually override EIP or not, right? So I'm gonna try and override EIP with four B's instead of A, so that we can actually differentiate whether actually it's been overridden or not. So 4 B's. I'm gonna create one. This is the message part. I'm gonna create one variable called buff. And buff will be actually what we can do. So we got 2012, and I will send. So what we can do is actually don't need to send it. Let's do it here. So, and I'm trying to find, going a bit advanced and trying to find if we can have enough space for our shellcode too. So I'm gonna send probably, because we sent 5,000 before, right? So we got 2,000. I'm gonna send probably another 700, 800. Probably send another 800 C's. Yeah, probably. Let's do 700. Any questions in here? Okay. So everything's all right. Let's do that. So if I do Python that, it's sending buffer now. Let's go check out our Windows machine. See, this worked perfectly for us. So you can see ESP has been overwritten with C, right? And EAX is overwritten with A. So we actually touched the EIP. If you see, like we have sent 2012 A's. Now EIP is 42, 42, 42, which is a hex value of capital B. See that? And now we have, and then after that we have all the C's. So if we scroll down here, I'll show you. So if we double click, see, so this much space we actually have to put our shellcode in this area. But in order to actually put our shellcode, we need to do another thing, which is called trying to find out the bad characters. So there's a different binaries have different way of processing their function, and the bad characters are different. By default, the null byte is 00 is a bad character because it's in C programming. It's actually a string terminator. So if you have the null byte 00 in your shellcode, what's going to happen is when the program is running your shellcode, it's going to end if it's find 00. So we will avoid that. So now what we can do is we need to find the bad characters. This is the next step from here. So now, hang on a sec. Yep. So we know how to, we know after 2012 bytes we have EIP, and we can control it. We can override the EIP the way we want to, right? So the next step is for us to find the bad characters. So let's close this, run it again. Attach chat server. Why you are like this? Okay. Running. Okay. Just a moment. Let's go back to our calling machine. So now we need to send bad characters, and we'll send that as actually, yeah. So instead of this C's, we're gonna send back bad characters in there because we want our shellcode to be located in this ESP stack. Does it make sense? Okay, let's find some. Actually, I do have bad characters. You can find, I think that does GitHub. I think this one. Yeah. So you can literally copy this. So this is essentially from, see, doesn't start from the 00 because we're already omitting that. We don't want 00. We know that 00 is null byte, and that's a bad character regardless. So let's copy that. And then we can do is, oh, sorry, my bad. Undo. Thing I need to do is paste. Sense now. So now we're sending bad chars. So we need to get rid of that, and we'll say bad chars as a variable, right? That should be good enough. So if we run it again, oh,
Shaifi, you misspelled the BAP character instead of.
Oh man. What did I miss? Oh, I said bad. Wow.
Yeah, BAB.
Nice. That works, isn't it? Bad. C-H-A-R. I think spelled right now.
It should.
Yeah. So now it's sending. Hopefully it has sent bad chars, if I'm not wrong. So we're still overriding EIP and everything. What we need to do, we need to go to ESP. Hang on a sec. Does it? Cancel. Yeah. So now this is pretty important. So right click on your ESP register and then do follow in dump. So here I need to change something. Happened with the, hang on a sec, hex 16. Yeah. So this is how it will look when you. So now from here we need to identify which are the bad characters are. So how we're going to identify is this is pretty manual stuff. Like you literally have to count the hex value. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So there's nothing's unusual, right? Here. So you need to actually go through all of them till FF, that if there is anything out of ordinary in this section. Any questions? This is really important, like especially if anyone's prepping for OSCP, this is where everyone gets stuck. If anyone have any questions in regards to bad characters, how to find it, you can ask now.
Shaifi, it's Bryce here.
Hey, Bryce.
What would be your, so what sort of strategy do you use, and knowing that it's quite manual? So what, is there something, that you look for in particular when you're trying to attack a problem like this?
Literally, so far the banners I've been doing, and I've been taught is to count them one by one. And I literally count them probably 3-4 times to make sure, because otherwise your shell code will not work. So see, give you guys a heads up. There is no bad characters in this binary. The only bad characters we have is 00. Okay. To give you guys a good look how actually bad characters works. If I go here, can you guys see this? Okay. So this is another binary which has bad characters. So see 1, 2, 3, and then 4 and 5 is, instead of 4 and 5, it's B0, B0. Right? So you have to note down that 04 and 05 is bad character. We cannot have these two hex values in our shellcode. So
Shaifi,
yeah.
in the chat, PB is asking how to identify them as bad characters. So I think like B0 means it's bad character, right?
Not necessarily it has to be B0. Not necessarily it has to be this. Anything out of ordinary. Like if you count 1, 2, 3, 4, instead of 4, there is something else in there. That 04 is your bad characters.
Okay. Yeah, he got it, PB. Yeah, thank you, Shaifi. Yeah, cool.
So if I go to the next, let's say I have identified this, right? So if you see here, so after 37, 38, and 39 is bad characters. Okay, so literally you have to count the whole thing, and you have to find anything out of ordinary in the stack or not, which doesn't go with the chronological way. Make sense?
Yes, thank you.
There's another trick. Let's go back to our windows. So what will happen is, what if instead of actually do it in Kali, yeah. What if I go here, see we got B0, B0, right? And then later on we have again 6, 7, 8. It's flowing normally afterwards, right? What if you come across something, it doesn't flow afterwards? Like if you see gibberish after B0, B0, what's gonna happen then? How are you gonna know that the whole stack is not bad characters? Can't be, right? So we need to, there's another trick, which is, let's close this. So then what we need to do is, let's say we found out 4 and 5 are bad characters, then we have to delete these from our script and run it again. Does it make sense? So when we will run, we will get rid of these 2 characters which are already bad and run it again, our stack will change. You will see, I'll recommend some practice binaries after this session. Then if you go through them, you'll see one of them has this sort of problem. Like you're trying to count bad characters, all of a sudden after B0, B0, you will see characters like this. So then it becomes really hard for you to identify which are the bad characters. So in that case, what you need to do is you need to get rid of your bad characters from your script and run them again. So the script will not encounter this for example, for 04 and 05. Make sense? Okay, now what we need to do, so now we need to find, well, now we know that our bad character is only 00, a null byte. There's nothing else. Everything's looking pretty clean. So we can use all these characters to develop our shellcode. That's our objective, and we can write EIP too. So now what we need to do is we need to try and find a function which actually jumps. See, we actually analyze the dump of ESP, right? So now we need to find a function which actually jumps to this ESP stack, where we will be putting our exploit shellcode, so that shellcode gets executed. Any question? If anyone doesn't understand what I'm saying. I think everyone's clear. Okay, let's run the chat server again. Unity, run it. Okay. Now I'm gonna use a module called Mona. You can install that in your local Kali VM. I'll give you the link. Hang on a sec. Where is the link? Let me show you first, then I'll give you the link later on for the Mona module. So this module will actually find out different DLLs in running within your binary. So from here, see the bottom section. So make it running, and now we need to find if we do modules, I think. So it's kind of look like this. Can you guys see it?
Yep.
Do I need to, I don't know how to zoom in this thing. Or if I do, I don't know. So if you can see it, when you're actually analyzing your binary, see these save SCH, ASLR, NXComp, OSDL, DLL, try to find whether these are all false first. So we need to find out which functions, which DLLs has all of them in false. Okay, so that we can actually put our shellcode and if we run it, nothing out of ordinary happens. Sometimes you can probably find safe SCH is true. With what that means is, see, in the beginning we send out 5,000 characters, right? And it overwritten everything. So if you have safe SCH enabled, it's not going to overwritten anything. So then you need to actually find out a limited space. Let's say you need to send the characters like 1,000, 1,200, 1,300, 1,400 to find out whether it's actually overwriting EIP or not. Instead of sending like 5,000 or 4,000, way too much. You like if SCH is enabled, if you send way too much buffer, it's not going to override EIP. And from your point of view, probably you'll be thinking, oh, it's not working. You know, the script's not working, or it's not vulnerable at all. So that's the function of SCH. So now we can see this is ESFunc DLL, which has all false. Another thing to look into in this section is trying to find a function which starts the memory address. It's not starts with 00. So that's another thing. If it starts with a 00 character, it's not gonna work. It's not gonna end. Like it always gonna take it as a null byte, and the exploit will not go further from there. Does it make sense? Okay, now we need to find out actually the memory space of this expfunc DLL. So we need to do mona find and dash s. Okay, before that, I'll show you something. There's another thing in MSF called Mozzem shell. MSF, I think that's MSF-NASM underscore shell. I think, yeah, that's the one. Let it run. Why it's taking too much time? Because we need to find out the location of jump ESP. So we're trying to find out some function which we can jump from the EIP to ESP, right? So we run JMP ESP. So if you write that, this is FFEF. This is the jump ESP location. So let's go back to Windows. This is always gonna be FFEF. So like more you do, you'll get used to it. Like I kind of remember now, it's FFEF. So XFF X X E4. That E4. No, sorry. X E4. That the module name we found out was a ESS func.dll. Okay, it's something wrong. Let's do it again. So mona find dash s xff e4 I think that's the one. ssps.func.dll. Okay. So see, now it has number of pointers of type xFFE4. So see these pointers, these memory address we can use to actually jump to, and these are all got ASLR SEH faults, right? So we can use one of these memory address and we can jump to ESP. Okay, let's write it down. The memory address is 6250114BF. So I'm gonna you can use any of them you want. I'm gonna use the first one because it matches with everything and it doesn't start with 00. So I'm happy with that. So what we need to do is we need to go back here. I already did that before. See 62501 DF. If you run that, hang on a sec. See, so this memory address goes to FFEF and it's jump ESP. So once we find this one, right, what we can do is now we can write our script. We can write our script and give that memory address to the script where our EIP is. So let's delete this. So what was it? Message. I'm gonna say GE equals to B, and we are sending a, what was it? 2012. No, we're sending 2012 in our message. Then we can actually use it as a, we can define probably we should define a variable called EIP because we are writing EIP now. So if we do EIP equals to, always remember in this part, because Windows memory address uses a little endian. So the memory address we have 62501 for DF, we have to write it backwards. So DF 145062. So let's make it our EIP. Sorry, where is it? Yeah. So now what are we gonna do? XDF x14 x50 x62, isn't it? Yep. So now we have now we have our EIP. So instead of, we send out B before, right? So instead of that, we're gonna send the EIP, right, as a variable, and then we send after this we have sent, let's send another 700 Cs. 700 B, whatever. Sorry. Yeah, that should overwritten the EIP with this memory address. I hope I have, let's see if it's running or not. Yeah, it's running. Go back there. If I send our buffer, that did not overwritten with that memory address. ASCII ESPs. All right, something I did need to check again. Hang on a sec. Run as administrator. Run as administrator, yes. Administrator, yes. Go back to Kali, checker. Yeah, I have done C, AIP. Okay. We can also probably put some knobs in here. For I'll explain. Knobs is it's X90 in a hex. So knobs are it allows. There's a thing called get PC execution routine in Windows. So this will bypass the get PC function of Windows, and it will run. It's sort of padding. So it will slide the execution, and it will land on there. So if I do knobs equals to X90, yep. And we can add some knobs here, knobs plus, then this is our space we want for our 2012. Yeah, this is the space we want for our code. Sorry, here we go. Let's check Windows again. I haven't attached anything. Chat server, make it running. Yep. Did we? Oh, my bad. Sorry, my bad. This is what happens every time. Trial and error is part of your life. Attach chat server. No. So what we need to do is we need to select this. So select that and press F12. So we are actually setting up a breakpoint. So here it's gonna stop. The execution will stop till here. So and now if we get it running, now it should hit the EIP. Yeah. See the memory address of our ESS func. It's on EIP. So this is a prime time for us now we know that we can actually hit this memory address, which is links to jump ESP, and jump ESP links to this clean lots of seeds, 700 seeds. So ideally, if we put our shell code in here in ESP, then we can actually get a shell, hopefully. Let's start again. Okay. Actually, no. To get a shell going. Actually, no. Let's test out something else before. Let's generate shell code first. So we can use MSF Venom to generate a shell code for us. I'll use Windows MSF Venom. So I've got Mirror before. Don't do that. Actually, I'm not gonna use Mirror. Let's use a normal shell. So shell, we're not gonna use a stage, unstage. TCP, and then we have to provide our host. L host equals to 192.192. Actually, it's in our memory already. That's nice. So we are providing our IP address. This port, I want to catch our shell. Exit func. Before I go there, let's not put the thread. Basically, what this function does is, when you run this shell with this function, let's say if we come here, we got our server running, right? So if we don't have that function and we run the exploit, this server will crash. So the point behind we use that this function is, let's say you're targeting another machine, so that in that side of from that side they can't really say that something's happening, although yeah, normal AV will pick that up. That's Shikata Nagai is an encoder. It bypasses some AVs, but not all of them. You can always use probably after Shikata, you probably use -I probably 20 to actually increase the repetition of encoding. In our case, we're not going to do it. And -B is to point out the bad characters. In our case, it's just 00. So let's generate the shell code. Okay. So now we have a shell code without these bad characters. Let's copy this. Now can go back here. Can paste to So this is our shellcode. So now what we're doing is we're going to replace this C with our shellcode. So and we can actually we can increase the knobs. So we put only one here. We can put probably 10 knobs for better padding. Then we'll have buff as our shellcode, which is here. Then we'll put another knobs, probably another 10, or let's do 16s. We have enough space. Why I'm saying we have enough space? See here the payload size. Can you guys see this? It's 351 bytes, right? And remember, we had 700 seeds. So we actually have enough space to put this shellcode in that ESP register. So let's do that. Actually, I don't want to write this like that. It looks bad. Because I'm doing knobs. Where are knobs? If I go here, put 16s of them. Okay. All right. So I have put in our shellcode in our script. Let's see. This is what we cannot run when you're running against. We cannot run debugging. Okay. Otherwise, you will not get a netcat session back. So let's cancel this. Run this as a administrator. So when you finally decided, all right, we got our EIP set, we know where we can jump, and then now we have our clean spot for our shellcode. So then the last step is to just run the binary by itself without attaching to your immunity debugger, and then run the exploit. So let's go back here and what was it, 9? So nc lvmp 9001. I'm listening to that. Fingers crossed. Hopefully we'll get a shell. Yep. See, if I do, where am I? This is my desktop. dir. So if we go back, the server is still running. We have exploited. We got control over this machine and our server binary. There's only you can only see if it's running somewhere, because not always this is gonna run on the desktop. Like if you're targeting another machine, so with the similar binary, what you need to do is now is to just change your shellcode. Sorry, hang on a sec. So all you need to do is, sorry, not the shellcode, here. You need to provide your target IP address and you will get a shell. That's it pretty much for now. But one more thing I do wanna show you, which let's do wanna show you what I was gonna show you. Just quickly, one last thing. Oh, it was running, right? Isn't it? Let's close it. Run it again. Immunity debugger. chat server. So remember we found out we inserted 700 extra space in here to locate our shellcode. What if we don't have enough space? Like we saw that we need to generate a Python shellcode. If I come here, if I do this, we see if to generate a Python shellcode, we at least need like 350 to 400 bytes, right? What if we don't have this space in our ESP? What are we gonna do? So another trick is see. All right, let's run the exploit again. Hang on a sec. Just quickly explain this. This is so now we don't have anything, right? We are just sending knobs and yeah, instead of knobs, let's see, let's send like 100 Cs and then knobs. That should be fine. See, we got just 100 Cs here, right? Which is not enough for our shellcode. We can't put a shellcode here. So if you ever encounter something like that, what we need to do is we need to find another space where we can actually put our shellcode, another clean space, another space in the stack which we can actually direct to. So we still need to find the EIPs the similar way we did. All we need to do is we need to put another. We need to break down our exploit. To be honest, we need to put another first stage of exploit in this clean ESP, which we can do with. Let me have a look. Just give me a moment. Yeah, we can actually insert a small code from like 7. It takes like 10 to 12 bytes. A really small code, and we can direct ESP to this EAX. See the EAX where we actually have 2012 A's characters, where we put our A's in there, because before EIP we have our all A's on top, and then it's actually point to like touch the EIP. So if you ever encounter, I don't want to go. It's a little bit tricky. You can give it a try. If you don't find enough space in your ESP, then the Mozzem shell from MSF Mozzem shell, you can actually find out the EAX, like jump EAX instead of jump ESP. Quickly actually show you. It's better to. If I go there, so that's actually part of your exploitation building. You need to identify how much space you have, and you also need to identify where EAX is actually starting, and is there any other characters in that EAX or not. So let's say if I have EAX in EAX, I have got like another 12 characters. Add EAX, comma 12. If I do this, it gives me this value. Okay, and then I can put this value in I can put this value in here, which will point towards EAX. Make sense? It's a little bit advanced, but I've just I have encountered probably once while doing the buffer overflow, especially in Linux, I think. So if you encounter something like this, always trying to find out in your stack there's other spaces which you can also link, and just try from then you just need to break down your exploit. Instead of putting one, you have to break it in different stages. So that could be your small first stage. If you do EAX, so this is the memory address for FFE0 is the memory address for jump EAX. So you can literally write this and that will jump from ESP to EAX. Hopefully I have covered enough, I think. This is it so far from my side. If anyone has any questions, I've been talking for a long time now, so just ask me if you have any doubts.
Okay, so I think we are good to end the session. So if there is any doubt, please do ask. We will be, I will ask Shaifi to stay online for another couple of minutes. And after that, we will end. And Shaifi, thank you for doing this session. And, yeah, it was a bit advanced for a beginner, but still.
Yeah. Sorry. Quickly, one thing before we close it down, just one more thing I just want to show. I forgot actually.
Yeah.
It will help everyone. If anyone wants to practice, Try Hack Me. I'm a massive fan of Try Hack Me. They have changed the learning process of hacking. Trust me. So they have buffer overflow prep, where you can practice all these. And I think this is a free room too. Yes, it is a free room. Check it out. This room's been designed by Tiberius. He's awesome. So just check this one out. Another one is this one. Do Stack Overflow Good from GitHub.
Yeah,
he
please
has a
share that
PDF.
on the Shaifi.
Sorry.
The link for the GitHub. Please share that on the chat.
Yeah. I'll copy everything. So this is a little bit different. And you guys can practice on this. I'll provide all the links here. He has a PDF, he has a binary, and he has all sorts of instruction. You can do. What else? This should cover everything. Like this will cover especially the bad characters part of the exploitation. Yep, this is it from pretty much. I'll show the link. I'll share the links in the chat room. That's one for the GitHub. Oh, sorry. Better send it to everyone.
Cool. So that's all from Shaifi?
Yes. Thank you guys for actually being patient for a long time.
And soon we will be, the LPTC will be coming back with another session with Sai Ashwin. He will be performing live Wi-Fi hacking, and I will make sure that the beginners will be able to understand what's happening with the wireless network, and I will force Ashwin to do a beginner-friendly stuff. So stay tuned, and I'm ending the meeting. Thank you for showing up.
Yeah.
Bye.
Thanks, guys. Thank you so much.
Thanks, Shaifi.
If anyone has any questions, shoot me in LinkedIn or Twitter. I'll try to help.
Yeah. And I'm ending the call.
Yep.
Thanks, Shaifi.
Yeah. Thank you.